Imagine being dropped into a world where direction itself no longer exists. No roads, no mountains, no trees, no landmarks of any recognizable kind. Just a frozen horizon stretching outward in every direction, identical and infinite, as if the earth had forgotten to leave any instructions for the people standing on it. In the Arctic, even experienced modern explorers have reported losing their sense of direction within minutes during whiteout conditions. When sky and ground merge into the same featureless white, the human brain loses spatial reference entirely. Without visual anchors, trained adults begin walking in circles without any awareness that they are doing so. For early humans, this was not an occasional hazard, it was seasonal reality. And yet the archaeological record confirms that human groups crossed these environments repeatedly, not stumbling through them, but moving with purpose, hunting systematically, migrating on schedule, and building seasonal movement systems spanning thousands of kilometers across terrain that modern navigation still sometimes struggles to interpret. They did this without maps, without compasses, without any instrument of any kind, which raises a question scientists are only beginning to fully appreciate. What if Arctic navigation was not merely a survival skill, but one of the first large-scale information systems our species ever built? Because the humans who learned to move reliably through the frozen world did not just survive extreme cold, they proved that humans could engineer certainty inside uncertainty. And that ability may be the deepest reason our species is still here. The Arctic is almost always described first in terms of temperature, and the temperatures are genuinely extreme. Winter air in the Siberian interior drops regularly to -50 degrees Celsius. Wind chill along coastal regions can push apparent temperature to -70. Exposed skin freezes in under 2 minutes. But anthropologists who have spent careers studying Arctic survival cultures are consistent on one point. Temperature was never actually the greatest danger. Uncertainty was. At -40 degrees, a wrong decision does not simply cause discomfort. It compounds rapidly toward lethality. Extra walking distance means accelerated calorie loss, and calorie reserves in Arctic winters were already dangerously thin. Additional exposure time means frostbite advancing faster than the body can respond. Missing a known hunting zone by even a few kilometers could mean starvation not immediately but 3 weeks later, when the reserves that should have been accumulated simply were not there. Think about what that actually meant for a family traveling in winter darkness. One wrong turn, one misread landmark, and the children do not survive the season. Research published through the Arctic Institute of North America estimates that traveling even slightly off optimal route could increase energy expenditure by 20 to 30%, a margin sufficient in genuine subsistence conditions to threaten group survival entirely. Navigation in the Arctic was therefore never convenience. It was biological risk management at the highest possible stakes. Every journey became a calculation. Distance against available calories, exposure duration against expected reward, known information against the cost of being wrong. Because when mistakes kill within hours rather than years, evolution stops rewarding strength. It rewards accuracy. And accuracy at scale requires something far more complex than muscle. It requires information architecture. Archaeological evidence gathered across Arctic Canada, Alaska, Siberia, and Greenland has fundamentally changed how researchers understand prehistoric movement in these regions. Early Arctic populations were not wandering randomly across frozen terrain, hoping to encounter food. They were operating inside structured mobility networks with identifiable corridors, predictable waypoints, and seasonal schedules that repeated with remarkable consistency across generations. The Dorset culture, flourishing from roughly 500 BCE to 1000 CE across the eastern Arctic, left evidence of coordinated movement across territories spanning hundreds of thousands of square kilometers. The Thule culture that followed them, the direct ancestors of modern Inuit peoples, operated networks connecting Pacific and Atlantic coastlines. Earlier Paleo-Inuit groups, dating back more than 4,000 years, used the same travel corridors repeatedly enough that certain archaeological sites contain layered debris from dozens of separate seasonal visits across centuries. Researchers at the University of Copenhagen, analyzing Paleo-Inuit site distributions, have described these patterns as evidence of cognitive mapping at landscape scale, the ability to hold and navigate enormous mental representations of terrain across time and space simultaneously. This was not exploration in the romantic sense we associate with that word. This was infrastructure. Not physical infrastructure in the form of roads or bridges, but cognitive infrastructure, the ability to move reliably across extreme and visually uniform terrain, using nothing but organized, transmitted, and continuously refined knowledge. Civilization is conventionally defined by the first cities, the first written laws, the first permanent monuments cut in stone. But Arctic archaeology quietly offers a different definition entirely. Civilization may have begun the moment that human movement became predictable. The first navigational breakthrough came from recognizing that the frozen landscape was not empty or random. It was patterned, and its patterns were readable by anyone trained to see them. Wind, the dominant shaping force of the Arctic surface, sculpts snow into elongated ridges called sastrugi. These are not random dunes. They align consistently with the prevailing wind direction for a given region, and in most Arctic zones that direction remains remarkably stable across seasons and years. To an untrained observer, sastrugi look like slightly irregular frozen waves, perhaps interesting but navigationally meaningless. To a traveler who had learned the local wind patterns, they were directional indicators as reliable as any magnetic compass, because they were the permanent physical record of atmospheric physics written directly into the surface of the Earth. Ethnographic research conducted with Inuit hunters in the 20th century documented navigators who could determine orientation and approximate location using snow texture alone, running a hand or sled runner across the surface and reading crystal grain, crust hardness, and ridge angle without looking at the sky at all. This is not intuition in any mystical sense. It is pattern recognition trained to extraordinary precision through years of deliberate environmental immersion. The underlying principle is pure engineering logic in its earliest human form, not changing the environment to suit human needs, but extracting reliable positional information from natural processes already occurring. Nature became instrument, wind became compass, snow became a readable data surface. This same fundamental principle underlies technologies from radar to satellite imaging to climate modeling. Early Arctic navigators discovered it first, and they discovered it because survival gave them no alternative. Direction is only the first layer of navigation. Knowing orientation tells you nothing about where food is, where ice is structurally safe, where underwater currents run dangerous beneath a deceptively solid surface, or where a storm shelter exists within survivable distance. Real navigation across thousands of kilometers of terrain that changes with every season requires memory at a scale that individual minds cannot sustain alone. This is why Arctic societies developed one of the most remarkable intellectual achievements in early human history: distributed oral geographic databases of extraordinary depth and operational precision. Indigenous Arctic cultures across the circumpolar world built place name systems containing thousands of distinct designations for environmental features, and these names were not simply labels. They were compressed data packages encoding ice stability assessments, animal movement observations accumulated across decades, freshwater access locations keyed to specific seasonal thresholds, dangerous tidal behaviors, and safe shelter configurations. Research by linguists working with Inuktitut-speaking communities has documented place name systems containing information that took modern researchers years to independently verify using satellite data and hydrological information, surveys. Each name was a data node. Each story attached to a location was an operational briefing. Each elder who could recite routes and their associated seasonal conditions was functioning as a living navigation database accessible to the entire group. Information theorists who have studied these systems describe them as structurally similar to distributed redundant storage architectures, where no single point of failure destroys the entire information set because knowledge exists simultaneously across multiple human carriers. In the Arctic, losing knowledge was not an academic tragedy. It was equivalent to losing territory, and losing territory in these environments very often meant losing the capacity to survive. Navigation in the Arctic also required reading motion, specifically the motion of other species sharing the same environment and responding to the same seasonal forces. Caribou, the dominant large mammal of the circumpolar Arctic, migrate in patterns consistent enough across millennia that early humans could use them as living directional signals in coating season, geography, and food availability simultaneously in a single observable behavior. The great barren ground caribou herds of northern Canada, some historically numbering in the hundreds of thousands, moved on predictable schedules between calving grounds, summer ranges, and winter forest edges. Seabird flight paths in coastal regions provided consistent indicators of land proximity and direction, even when coastlines were invisible through fog or ice haze. Ringed seal, breathing holes in stable sea ice, marked zones where ice thickness was reliable enough for safe travel. This is precisely what modern cognitive science calls environmental integration, combining multiple, individually ambiguous signals into a single, high-confidence decision model. No single animal sighting determined direction. No single snow formation confirmed position, but a trained navigator reading terrain, biology, atmosphere, and sky simultaneously could build a location estimate with precision repeatedly sufficient for survival. What strikes researchers who study this is that early Arctic humans were performing this cognitive operation tens of thousands of years before science gave it a name or a mathematical framework. Because extreme environments force the brain to develop adaptive prediction capabilities that later, in entirely different contexts, became the foundation for scientific modeling itself. The Arctic did not just host early human intelligence. It may have been one of the primary pressures that sharpened it into something extraordinary. Above the Arctic Circle, winter removes the sun from the sky for months. At Barrow, Alaska, the sun does not rise for 67 consecutive days. At Eureka in the Canadian high Arctic, polar night lasts nearly 4 months. Without any artificial lighting beyond small oil lamps, this was not an inconvenience. It was a total transformation of the perceptual world, a darkness so complete that entire communities had to navigate, hunt, and travel across moving ice without any of the visual cues modern humans depend on entirely. And yet the evidence is clear that Arctic populations did not stop traveling during winter darkness. They adapted by expanding their reference systems upward into the sky itself. Stars became directional anchors with a reliability no terrain feature could match, because stars do not change with snowfall or seasonal flooding. Polaris sits approximately at the celestial North Pole and was recognized by circumpolar cultures as a fixed orientation point requiring no instruments whatsoever. Experienced navigators learned to read the entire visible sky as a dynamic three-dimensional reference system. Different constellations indicated not just direction but season, which told a trained traveler where specific animal resources would be concentrated and which routes would be accessible. The low solar arc near the horizon during polar twilight provided orientation through subtle light gradient changes that skilled observers could read even without seeing the sun directly. This integration of terrain reading, atmospheric signal processing, biological pattern recognition, and astronomical observation constitutes a genuine technical achievement. A three-dimensional navigation system uniting surface, atmosphere, and sky into a unified positional model. Long before mathematics formalized coordinate geometry, human survival in the Arctic already depended on a working, intuitive version of exactly that system. Alongside these perceptual technologies, Arctic peoples constructed something more tangible, a distributed physical information network embedded directly into the landscape. Stone markers known in Inuktitut as Inuksut were built across Arctic North America in configurations and locations encoding specific operational meanings. Some marked safe crossings of frozen rivers or sea ice passages. Others indicated food caches that could sustain a traveling group through a sudden storm. Certain designs communicated proximity to hunting grounds, while others marked territorial boundaries or sent signals between groups traveling separate routes that might not encounter each other for months. Some Inuksut were constructed specifically to direct caribou movements during hunts, placed along ridgelines to create the visual impression of human presence that guided herds toward kill sites where hunters waited. Archaeological surveys in the eastern Canadian Arctic have identified Inuksuk sites dating back over 1,000 years. What these structures represent collectively is genuinely extraordinary. Before written language, before any information technology as we conventionally define it, Arctic peoples were operating what can accurately be described as an analog information network distributed across thousands of kilometers of terrain. Each marker was a node transmitting stored knowledge to any trained receiver who encountered it. The network as a whole encoded route, safety data, resource locations, group communication, and territorial information across a geographic scale comparable to a modern regional infrastructure system. Civilization is most often defined by monumental architecture built for permanence, but Arctic societies demonstrate a different and perhaps more fundamental definition. Civilization is the capacity to externalize knowledge into systems that outlive the individuals who built them. By that measure, the Inuksuk network was civilization in its fullest expression. The most powerful navigation technology ever developed by Arctic peoples left no physical trace in the archaeological record because it existed entirely within human minds. Researchers who have worked with master navigators from traditional Arctic communities describe a cognitive capability that appears almost impossible from the outside, but is upon examination the product of years of systematic environmental immersion beginning in early childhood. Experienced travelers could move across hundreds of kilometers of visually uniform terrain using accumulated sensory memory built over decades of precise attention. They tracked wind pressure gradients against exposed facial skin as they moved through different topographic features. They read the exact quality of available light during specific hours of specific seasons. They processed the acoustic signature of sled runners crossing different snow densities the way a trained musician processes harmonic relationships. They registered slope changes of less than 1 degree across apparently flat terrain through proprioceptive feedback too subtle for an untrained body to detect. Neuroscience research on expert navigators, including landmark studies of London taxi drivers who must memorize one of the world's most complex street networks, consistently shows measurable structural changes in the hippocampus, the brain region central to spatial processing and memory consolidation. If navigation training produces measurable neurological changes in modern study participants over relatively short periods, what might sustained navigation pressure across thousands of years of evolutionary selection have produced in populations where navigational failure directly and immediately meant death? The Arctic may not merely have tested human cognitive capacity. It may have been one of the primary environments where the advanced spatial and systems reasoning that distinguishes our species was actively shaped into its modern form. The navigational systems described across these segments share one property that separates them entirely from every physical adaptation other species develop to survive the same environments. They are scalable. Polar bears are extraordinary Arctic survivors, cold adapted at a biological level human physiology cannot approach. Musk oxen have endured Arctic winters for hundreds of thousands of years through pure physical resilience. But no other species can take what one individual learns and transmit it to others in a refined and improved form. No other species accumulates navigational knowledge across generations in a way that makes the 100th generation meaningfully more capable than the first. Physical adaptation hits a ceiling defined by individual biology. Human information systems have no such ceiling. This may be the real turning point in human evolutionary history, not toolmaking, not language alone, But the moment navigation became humanity's first operating system, a shared platform of environmental knowledge that every member of the group could access, update, and transmit forward in time. Homo sapiens did not outcompete Neanderthals, who were physically stronger and had lived in cold environments far longer, or Denisovans, who showed genetic evidence of superior cold adaptation by being physically dominant. We outcompeted them by building information systems that scaled beyond the individual. The Arctic forced our ancestors to become the first information engineers in human history. And Arctic navigation was not just a survival technique. It was the prototype of the compounding knowledge architecture that would eventually produce cities, sciences, and the civilization you are part of right now. So how did early humans navigate the Arctic without maps? The honest answer, supported by archaeology, cognitive science, and ethnographic research across circumpolar cultures, is that they did not lack maps. They built them in a different medium entirely. Maps made from wind direction and snow texture instead of paper and ink. Maps made from stellar positions instead of magnetic needles. Maps stored in oral traditions and apprenticeship systems instead of written databases. The information was real, the accuracy was genuine, and the reliability was proven across thousands of years of successful navigation through one of the most demanding environments on the planet. Every modern navigation technology, from maritime charts to GPS satellite networks, follows the same fundamental logic Arctic peoples refined across millennia. Reduce uncertainty by collecting environmental information. Increase predictability by organizing that information into transmissible systems. And extend capability by sharing those systems across generations. The architecture is identical, only the medium has changed. The same human brain that once read wind patterns in frozen snow now reads signals bounced from satellites 36,000 kilometers above the Earth. The same cognitive system that memorized thousands of place names encoded in oral tradition now stores them in servers. The instrument changed. The intelligence behind it did not. Perhaps what Arctic navigation ultimately reveals is this: humans do not dominate this planet because we are the strongest or the fastest. We dominate because we are the species that learn to treat uncertainty itself as a structured problem and then build systems capable of solving that problem persistently for every generation that follows. The people who first proved that principle were walking across frozen ocean in total darkness thousands of years ago, reading stars and wind and ice, finding their way home through a world that offered no margin for error. They were the first engineers of human knowledge, and everything we have built since then is built on what they figured out in the dark. If you find these journeys into the hidden intelligence of our ancestors as compelling as we do, consider subscribing to Prehistoric Shadows. Because the most important inventions in human history were not always made of stone or metal. Some of them were made entirely of memory, and they lit the way through the dark long before we ever thought to look up at the stars and call it science.